Welcome to day 11 of the 2023 Advent of Code. So today's problem is yet another grid problem. So let's just grab the grid first. And let's see what we have to do. So we have a bunch of galaxies marked as pound signs and empty spaces marked as dots. Okay. We want to figure out the sum of the lengths between every pair of the path between every pair of galaxies, but the universe is expanding. And so only some space expands, so notably any rows or columns that are empty should be twice as big. So let's grab those empty rows and columns. So the empty rows are just each row index r for r row in enumerate grid if every character in row is equal to a dot. So if this is true, then the row is empty. Likewise, the empty columns are each column index c for c call and enumerate zip of star grid if all characters are dots. And what zip does here is zip takes one or more arrays and goes through them column by column. So essentially it iterates through the first element of each list, and then the second element of each list, and then the third element of each list, etc. So that gives us our columns. So now we know where the empty rows and columns are. Starting with this expanded universe, any rows or columns that have no galaxies should actually be twice as big. So you might be tempted to just modify the grid, but from experience, it's already obvious to me that part 2 is just going to make it like a lot bigger, like 1,000,000 times or something like that. So you could do it just by expanding the rows. In fact, that's how I did it at first. The reason I did it that way is because I knew that I would be sacrificing a bit of performance on the part 2 leaderboard by needing to rewrite parts of my solution, but that I would probably get back more score on part 1 by writing a solution faster. In the end, it turns out that I probably could have done the part 2 approach in part 1 in about the same amount of time and just saved myself more time on part 2. But I never claimed I was the best at AOC. So let's just do this with part 2 in mind. Basically, we're not going to modify the grid, we're just going to do this somewhat intelligently. So now, between every pair of galaxies, we want to find the length of the shortest path between them. So basically, it's just the Manhattan distance between them. As we see here, we're not counting diagonals, so it's just vertical and horizontal steps. So it's just the Manhattan distance. Let's first see how many pounds there are. There are 448 galaxies. And so if we take 448 times 447 divided by 2, that gives us the number of pairs in total, which is 100,000. So we don't need to do anything more clever. We can just iterate through each pair. Okay. And so now we want to get the positions of the galaxy. So let's say points is going to be RC for each row, for each column, if the character is a pound sign. So that gives us the coordinates of our points. And now we just go through each pair. The way we can do that is for ix in enumerate points, we now have a point x, and we also have its index I. And so then we can do for y in points up to and not including index I. That basically means that we won't count any pair twice, and we won't pair any point with itself. Basically, each time we look at a point, we only look at a second candidate point strictly to its left. Let's also unpack it into R1C1 and R2C2, the row and column coordinates of the first and second points. So now the way we're going to do this expansion thing is we're just going to loop through each row between the two. And for each row, if it's empty, we add 2 instead of 1. So we can say for r in range R1 to R2, we need a total value. Total plus equals 2. Let's isolate this variable. Scale equals 2. Scale if it's an empty row, otherwise 1. And then for each column as well, total plus equals scale if C is an empty column, else 1. Also, one thing we do need to keep in mind is that R1 and R2 could be out of order, so we're going to do min R1 and R2 to max R1, R2. And same for the columns. This just ensures that even if our columns or rows are out of order, that we will not be looping through an empty range. And so that's all there is to part 1. Indeed, for part 2, it's just replace 2 with a million. And assuming you don't typo a million, the second part is also fairly easy. And so that's really all there is to this problem. So, relatively short video today. I kind of messed up with my intuition of what the fastest way to do part 1 and then get a decent score on both parts would be. It turns out that it would have been easier to just do the complete solution from the beginning. But with a bit of foresight, you can see that the fact that scale is 2, allowing you to modify the grid, is a bit suspicious. And part 2 is, generally speaking, to check how adaptable your part 1 solution is. And so in this example, it's not a stretch to assume that it's just going to ask you to adjust the scaling from 2 up to a high number that you cannot just iterate through. Yeah, so in any case, that's all for this video. Thank you for watching, and I hope you enjoyed.